Log on, tune in, find out. Another good idea from Cambridge.
But, very good. Excellent. Well, conversion. Very good. Thank you. Sorry for the delay. My name is Idris Titi, has been introduced here, and I am a friend of my old friend. So we're not old friends, but in any case, it's a pleasure to be here. Back to the Newton Institute. I was here many years ago, and I keep coming to because of the invitations of good friends. I'm not a numerical analyst, however, I'm working more in PDEs and Navier-Stokes and applied mathematics. However, once in a while we run into mutual interest, because at the end of the day, Navier-Stokes is not an equation which we can analyze completely without numerical help, and once in a while some ideas coming due to phenomenon in nature like oscillations and fast rotations and so on and so forth, and therefore you find yourself, you need to really try to deal with the equations that you have at hand. And since the equations at hand are completely difficult, you always go to baby models or to something easier that you can understand, hopefully, and then you find yourself that there's many other people have been doing things which are similar. You learn from their experience, and hopefully you can have some exchange. So I'm going to basically give sort of tutorial, because I would like to set the stage for what I'm going to talk about. I appreciate if you bear with me, at least maybe at the very beginning. Some of the stuff would sound trivial, however, I need that in order to set the stage, so basically some of the concepts will become clear. So the background, I'm going to talk about the classical theory of Tikhonov-Levinson. Of ODEs, I'm going to do ODEs, but I'm going to, at the end of the day, discretize some PDE. I'm going to give some motivation examples of limit cycles when you have fast oscillations. And then I'm going to use the notion of Young measure in order to describe the fast dynamics. And this is basically the upshot of the talk that I'm going to use. And then I'm going to look at fast, slow systems without have separation of fast and slow state variables. I don't know who is the fast guy and who is the slow guys, yet I know that the system has some fast features and slow features. But I cannot identify who is the fast guys and who are the slow guys, so I could really simulate the slow guys. And therefore, still, can we identify some objects or some features, and we can really develop some numerical schemes to compute them. Now, right from the very beginning, in order to set the ground and to put things, let me give you metaphorically, and I hope that there's some people here from kinetic theory, my understanding, that there's a different program. Just to have the metaphor at hand, imagine that we have the Boltzmann equation, which is basically that what everybody have, molecular dynamics or something. Everything is moving like crazy. And yet, at the end of the day, we know we cannot track every particle and particle. There's tens and hundreds of thousands of them. So none of the particles is slow and none of the particles is fast, or all of them are fast. Can we take combination of them and check which one, like maybe take variables, change of variables of the state variables, and find what are the variables? And the answer is we cannot do that. So what is instead, which has been done by physicists over the year, and this is basically, I'm setting the ground for what I'm going to talk about, because the features are the same. You have to get out of the system. Go out, don't interact with those individual things which are moving, and look, as mathematicians, or physicists in that case, from different perspective. You have to look at it from different framework. And the framework is, let's look at invariant measures of these dynamical systems. And we look at the invariant measures of these dynamical systems. These are kind of like quantities which are basically take things in the average. Now, what happens is you cannot sometimes compute these invariant measures, because, I mean, invariant measure is not an object which is, you can discretize it numerically and have something at hand. So what do? Maybe you try to look for some numbers from this invariant measure, like a moments, like the average, the expected value. Maybe the first moment, maybe even the second moment. The problem usually, in general, if you write an equation for the average or for the first moment, you don't get a closed equation. However, the miracle happens that in the case of Boltzmann equation of particles, when you look for the first three equations, the expected value is the density of the fluid, the first moment is the velocity of the fluid, and the second moment is the energy of the fluid. And under certain circumstances, without getting into details, we happen to know at certain parameters goes to 0, you get a closed system of equations for these first 3 moments, and this is exactly the Navier-Stokes equation. And these are slow features of this particle which is moving like crazy. And these equations we have at hand, and therefore we can compute with them. So, in order to understand what happens to this complicated system, I cannot deal with the individuals in this community. I have to look at certain features of this community, like invariant measures, but even then I cannot do it. I have to deal with some moments. And if I'm lucky, I can basically get closed system. If not, I have to approximate that and so on and so forth. So we have to step away from the system and look at features. And that's the title, looking at slow features of the dynamics, not individual state variables. This is the big philosophy. Now you can bear with me because I have to set the ground through examples about to go where I'm heading. I'm heading to those features, but I need to identify them for specific systems, and that's the purpose of this talk. So I hope at least I conveyed the message at large. You can take off if you like, or you can basically take a nap or whatever. So let's start from very, very classical case, which is the singular perturbed system. And this is basically an ODE, system of ODEs, and system of this is the fast one. You have 1 over epsilon, so the derivative is like 1 over epsilon is very, very fast. I'm looking at what happens when epsilon goes to 0. This is the classical case. I have to start from 101, from the very beginning. So this is the system that we have at hand. Now what happens usually? Usually what happens, computing solutions of the above system is very costly because when epsilon is very small, because you need to take time step delta t like epsilon. This is not the right audience to tell them that. You have experience with these kind of features. So our goal becomes, can we find the limit behavior of the solution x epsilon y epsilon as epsilon goes to 0? And moreover, what is the equation of motion for the limit that governs the limit? Because if I find an equation of motion for the limit, I don't have epsilon anymore at hand, and then I can approximate the solution x epsilon y epsilon by the solution of the limit equation if I can, because there's no more epsilon, there's no more scale. So can we develop even efficient numerical schemes or algorithms for computing the above limit behavior? So the classical theory of singular perturbation method, namely it reduced the limit by saying, well, let's plug epsilon equal to 0, and therefore we get an algebraic differential equation. This is the classical theory. Now under which circumstances, as many of you know this works, when you solve this algebraic equation, you get y function of x. Supposedly you can have one solution, but usually you could have many folds, and therefore there are many solutions. But suppose you have solutions, and now under which circumstances one have a situation. So a particular class of the Levinson, in particular, as I said, the classical Levinson-Tikhonov approach assumes the following condition, which we call assumption AFP. It will become clear what's AFP for. The region of interest in the analysis, where for x fixed, x is basically the slow variable, the solution of the equation, this fast equation, notice I rescale the time. So this is the fast equation. It converges to a stable solution y of x. So let me give you a picture. That's why I lifted the board a little bit. So the algebraic equation g of xy has a solution. So this is the y variable, and this is the x plane, and there is a manifold here. This is y of x, which is a solution g of x, y of x is identically 0. So what's the assumption? For every x fixed, I have y of x here, and now I fix the x, and I look what happens here in this plane. Okay? And I look for the fast dynamics, for the y dynamics. And the assumption is that this fixed point, when x is fixed, is attracting. That's the classical theory. Now what happens in this case? Of course, because you are fast dynamics, you come very fast to this manifold, and then you'll be tracked by the algebraic differential equation. And this is the classical theory. So you need to be attracted all the time in this direction. So this is the assumption that you have. This is the classical Tikhonov Levinson theory. It says that which is therefore this is algebraic equation has a fixed point, and this fixed point is stable, and that's why the word AFP, it's basically asymptotically fixed point, which stands for asymptotic fixed point, which is stable for this. This is the classical theory that you have to have g of xy has a solution. The solution is a fixed point for the fast dynamics, and the fast dynamics is attracting to that fixed point, and therefore this classical theory, there is nothing happens. Now let's take some examples, which is very simple examples. So I'm going to consider this system. This is the slow dynamics. The xi is the slow dynamics, and the eta is the fast one. And I'm going to add a nonlinear potential f here, which is depends only in eta 2. So I'm going to consider these particular cases. So I'm going to compare now what happens when epsilon goes to 0 of the dynamics with the fast. So I'm going to consider two different potentials. The first potential fs, and s will stand for stable, and fu and u is for unstable. Okay? So notice the difference between the two potential is exactly this sign, minus eta and plus eta. Very simple example. So in the stable case, I follow exactly what I have been mentioned here. When it confirms basically the theory, the analysis of the fixed point of the Levinson and Tikhonov, namely you can solve explicitly for the three variables xi equal xi1, xi2. When it is kept fixed, the dynamical system, the fast one, converges to the unique fixed point minus xi1, minus xi2, and 0. And therefore, you converge to there. And one can, in this particular case, this point is asymptotically stable, and everything is nice. That's why it is called the stable fs. And as a result, one can show, in this case, that the solution is slaved. You come very fast to this manifold, and then you go parallel to the manifold when epsilon is very, very small. That's basically what happens. So therefore, the solution of the algebraic differential equation mimics what happens in reality. But there is an assumption that you need to be stable. Otherwise, we will see what's going to happen. So as I said, this is the situation. And now, this is the fixed points that you have. The solution of the algebraic equation, you plug it into here, and this is basically give you the slow dynamics. This is, I have separation of scales, and I told you I need the separation of scales to understand what are the limitations, how much I can push it, because later I'm going to not assume that, but still I would like to learn something from this. So this is the situation when epsilon goes to 0. So now what happens when I look at the unstable case, when I have plus eta here? So in this particular case, if you apply this system is not the system that I mentioned, this example is not just an academic example. It appears in some applications in mechanics, and therefore it has been studied by some people. So in this case, the Levinson-Tikhonov theory does not apply. So this fixed point that I just mentioned to you, when you fix it, you fix the slow variables, then what you get for the fast dynamics, you don't get stable fixed point, you get the van der Pol system. And the van der Pol is the classical textbook material for the Poincaré-Bendixson theory, like basically when you go to something which is a limit cycle. So in this case, the fixed point is unstable, but the limit cycle is stable. So whenever you start, you don't go to a fixed point. The fast dynamic will take you into something very oscillating very fast. And now what happens is the following. The fast dynamic is going very fast to a limit cycle, but the slow dynamic is going to be drifting. So what we're going to have in general, we're going to have like a tube. The cross sections need not to be circles. They're limit cycles, really limit cycles. They could be like twisted, and therefore the full system is going around a tube, which is basically going to be drifting slowly. So now the whole idea is how to describe this mathematically and how to develop numerical techniques to compute what happens in this particular case. So therefore, the stationary point determined by the algebraic equation is unstable in this case with respect to the fast dynamics. In particular, we do not have, this manifold is not attracting, as I mentioned here. So in this case, what we have is a asymptotic limit cycle. So under the assumption of a asymptotic limit cycle, in the region of interest, the solution of the fast dynamics is converging to a limit cycle. So this is basically the assumption under which I'm working in this example, and this can be tested. You give me a slow variable fixed. In this case, the fast dynamics goes to a limit cycle. Now, how do we describe a limit cycle? We shall call it gamma x, because for every fixed x, I have a limit cycle. For every cross section, I have a limit cycle. For every cross section, I have a limit cycle. For every x, I have a limit cycle. How do I describe a limit cycle? And now we will basically start doing a little bit, developing the framework that I'm talking about. So this is basically consistent with the work which is in the Bogolyubov, Mitroglovsky, and Peter Yegin. So let me just to give you a feeling of why we need fast develop efficient algorithms. If I take the examples that I mentioned to you just a minute ago, and for different values of epsilon, you can see in the stable case, in order to converge and to do simulations, you get basically, this is the time it takes to do the simulation. However, in the unstable case, you can see the smaller the epsilon, because you go faster and faster to start making this tube drifting, you need to go more and more around the circles, and therefore it takes longer and longer and longer time, longer and longer time, and therefore there is a need to do some simulations which are more efficient in order to compensate for what happens here. And this is basically the purpose of this lecture, as I will describe it in a minute. So under the assumption of limit cycle in the space Rn cross Rm, Rn is the slow ones and Rm are the fast ones, I'm assuming the following, that for every fixed x, which is a slow quantity, an initial condition y for the fast quantity, I look for the fast dynamics. There's no epsilon here, I'm looking for it as dynamical system. I rescale the time, I look for this, and as s goes to 0, I'm converging to a limit cycle. This is the underlying assumption. Now the question, how do we describe a limit cycle? So one way to describe a limit cycle is basically the way we know it. It is a periodic function. Gamma, for every fixed x, is function of time with period tx. This is the way we are used to describing a limit cycle, okay? So this is basically one way to describe a limit cycle. However, because I'm interested in dynamics, it's not enough only to give me that the limit cycle is a loop. I would like to know when I go fast on the loop and when I go slow on the loop. I would like to know how much time I spend on this portion of the loop, how much time I spend on this portion of the loop, and how much time I spend on this portion of the loop, because after all, I would like to represent dynamics, not only just, oh, I have a tube. Telling me that the limit is the tube is fine, but I need to know how much time I'm spending on the upper part of the tube and on the lower part of the tube, because I have some implications for that. So a different way to represent the limit cycle with the dynamics is basically through a measure. For every fixed x, I have a measure which is supported on the limit cycle. And now the measure tells me how much time I spend on every portion and each arc of this particular thing. So this is a different way to present it. So it's a closed curve. So the distribution mu x is a probability measure supported on gamma h, which assigns for each measurable subset the proportion of time that I'm spending on that. This is a different way to represent a limit cycle. Okay, it takes this mu x, inherits in it a dynamics. So such measures usually called Young measures, okay, or an example of a Young measure, because for every fixed x I get probability, for every x I get a probability. So this is basically, this is for every point x, it gives you like the probability distribution here. This is a description of a Young measure. Like for every point here x, you give me the histogram or the PDF. For every point you give me the PDF. So therefore they are marching, they are functions of PDFs depending on x, parameterized by x, by the slow variables. Okay, so that's basically the way I would like to describe these things. So a connection between the measure and gamma is given exactly by this formula, namely that if you give me any subset C in the space, I look the portion of time, lambda is the Lebesgue measure, I look to the proportion of time that I'm spending on this particular arc. This is exactly the definition of this particular. I basically mentioned that in words. Now this is the connection between the two descriptions, the gamma description and the mu description. Notice the mu is an invariant measure for the fast dynamics, and this is very important. So this approach was investigated by Arstein and Vigodner. So if I denote by x epsilon, y epsilon, the solution of the system that I mentioned to you, under the assumption that the limit cycle is the asymptotic limit, the goal is to describe the structure of the limit as x epsilon or y epsilon as epsilon goes to 0 over some interval. I would like to describe the tube. Okay, we know that the limit, basically you go to limit cycle, and then the tube is basically drifting slowly by the slow variables, the centers are, but I would like to describe it in a different way and try to understand how things are drifted. So when referring to the limit cycle given above, we can use either description. Also, we need to know, because my point is to see what happens as x epsilon goes to 0 and y epsilon goes to 0, I need the notion of convergence of measures, and this will become clear in a minute. So here is a theorem. Under the assumption of limit cycle, the x epsilon, namely the slope component of the solution, converge as epsilon goes to 0 uniformly to a given function. The slope component x epsilon, under the assumption that, namely, the fast dynamic going to a limit cycle, and the slow one is basically converging to some function x0. Now, my goal is to know the equation of motion for this one, and this equation of motion is exactly the averaging. I take for every fixed x, I have the limit cycle limit. I take the time average with respect to s, and therefore I get a vector field, and this is the vector field which tells me how things are really advancing. Okay? Or alternatively, instead of using the description of the limit cycle as a curve, I can use a measure, and now the measure is supported in the whole space. It is defined in the whole space, but supported on the curve. And therefore, this is an alternative approach for basically this description. And in fact, I'm not telling you anything new. This is the classical averaging method. Okay? So the slow variable is moving according to the average quantity. And here's basically the $1 million question. Everybody in all the textbooks in the world, they tell us about how does the slow dynamics is moving. Does anybody describe what happens to the fast dynamics in this case? Of course, people says we're not interested in that. Why? Why not, or why yes? I would like to see the full picture as a mathematician, okay? The whole idea is, yes, we found the slow quantities, how they're moving, and we have an equation for them, and we are satisfied, and this is what averaging method about. But all of us, we basically, over the years, have ignored completely what happens to the fast dynamics because it's not handy. Notice here is underlined point. X epsilon converges pointwise to x0. But what happens with the y epsilon? Going very, very fast. And the idea is the mathematical framework tells you that you shouldn't look at y epsilon as functions converging to a function, because they will not converge to a function. But you should think about them as measures, a delta measure. Every curve, every function, it's a delta measure supported on the curve. But it's becoming more and more condensed because oscillating like crazy, and should think about it in the context of measures converging. So the fast dynamics does not converge to a function, but as measures converging to a measure. And this is basically the mu of x that I'm talking about. This is exactly the limit of the y epsilons in the context of measures. And this is very important later when I'm going to talk about other things. That here basically I'm telling you that the x part, you tell me until now, nothing you knew. But everybody ignored and did not want to look at the y because we couldn't describe it. But as mathematicians, we have the way to do it. It is a Young measure. The limit is a measure in the context of measures. What can I do with it? How can I use it? This is something to be able to do. So the limit structure of the fast dynamics is more delicate, as I said. So we said, in general, x0 is not, if it's not a constant, y epsilon does not converge pointwise. What one can hope is to identify the limit topological location of the trajectory, which, as I said, is a tube. So the topological limit would be tubes. This is basically, you expect x epsilon, y epsilon to converge to trajectories which are here, which is like tubes. The x epsilon 0, this is the limit. And gamma, for every x you tell me, I get this limit cycle, and therefore the description topologically are tubes, which are drifted or parameterized by this particular thing. And the x epsilon is the limit here. However, if I look into more quantitative description, not topological description, because I need it for computations, so a quantitative convergence is that this part formed by resorting to the mu epsilon, as I mentioned, and indeed the family of mu x0 is parameterized, the time in t in this interval. These are called literature Young measure, and this is describing the limit of the limit cycle. So again, as I said earlier, so the mapping y epsilon can also be viewed as a degenerate Young measures, namely a Dirac measure, delta y epsilon dy. And as epsilon goes to 0, I shouldn't look as y epsilon converging to a function, but I should look at this family of measure converging to a measure, and this is exactly the measure mu x. So to give you like a cartoon of what happens, This is basically a function y of epsilon. It's oscillating rapidly and more rapidly. And you can see at the limit, I don't converge to a function, but you can see I describe it as basically how much time I'm oscillating and how much time I'm really spending here. So I converge into a probability measure, which is a Young measure for these kind of things. And this is the that we have to keep in hand. So your user representation in these schemes is converges in the sense of measure. So as I said, the y epsilon will converge to mu x0 of t, where x0 is the pointwise conversion. So in computations that we did with Artstein and Lynshitz, at that time she was a master's student, this is the system which is the unstable system, and I would like to see what happens when epsilon go to 0 to this particular limit. Of course, I'm looking for the limiting behavior. So this is just to give you a transit. You can see because the limit cycle is stable. You start any point, you converge to limit cycle. This is just to give you some feeling. So this is the limit solution as epsilon goes to 0, because we know how to compute it. This is for small values of epsilon, and this is even for smaller values of epsilon. You can see that for different values of epsilon, this is the c1, c2, these are the slow variables. You can see that they are drifting slowly. They are not really on a curve, straight curve. They are basically in helix, and around each one of them you have a limit cycle. Okay, so they are really, you can see that for different values of epsilon, it's converging to the limit as we've been describing. And this is basically the fast dynamics. It's a zoo. I mean, if I tell you like, oh, here is all the information you want, x and y at the same time, you can see that I cannot really extract any information from this. It's just a zoo. However, you should look for every slice. Every limit cycle is a measure. And this is basically a way to make cataloging, if you want, classifying this particular mess of data. We take another example. Okay, this example looks like complicated. However, you can make change of variables in order to see things looking nicer. And if you look the change of variables like into polar coordinates, you can see this is basically the slow and this is the fast. Again, in separation of variables, you can see easily now that you converge, for every the fast dynamics converging to a limit cycle with radius exactly x1 when x1 is positive, and the angle is going very, very fast. So this is clearly describing this particular feature. So again, these are the slow dynamics. So for different values of epsilon, but this is at the limit when epsilon go to 0. And you can see that for small values of epsilon, you're getting closer and closer to the limit value. This is the solid line is epsilon 0.1. Okay, that's why it's far away from the reality. But the very, very solid line is in the heart of the matter, and this is the slow quantities. And if I look for the fast quantities, in this case it was honest to goodness circles, not only limit cycles, because r equals x1. And look, here you see them. They're basically, when x1 is moving, you can see them, they're coming in and out, in and out. And this is basically the fast dynamics which can be done. So, as I said, the general fast dynamics of compact attractors. So here's the general theory to summarize what happens. I gave you the example of a fixed point. How does the fixed point comes into here? The measure, what happens with the measure? In a limit cycle, it's a measure supported in the limit cycle. What happens when I converge to a fixed point? It's a measure at one point. It's a delta function. So in this case, when it's a delta function, the measure, on a point, not a delta function on a cycle. So in general, basically here is one can, under this general framework, one can have the following situation. Suppose I have separation of scales, and suppose for every x0 given and y0 given, if I look at the fast dynamics for each fixed x, the domain of interest is compact attractor with unique invariant measure mu x. This is a very important assumption, unique invariant measure, okay? And I will make a comment in a minute about that. Okay, suppose I'm under this assumption, then what can I conclude? In this case, one can show that under this assumption, the x epsilon will converge to some function x0. x0 will be the measure, the average with respect to mu. When it was a limit cycle, it was the classical averaging theory. But now nobody said that the attractor is a limit cycle. It could be a Lorentz system, for example. It could be chaotic. But it has an invariant measure, which is unique. This is an underlying assumption, mu of x. Then the slow dynamics is basically drifted by this mu of x, which is coming from the slow dynamics. And mu of x is the limit of the y epsilons when they are viewed as measures. So mu y epsilon converging to this particular case. Now I would like to basically pause here for a second and go back into this underlying assumption. This underlying assumption is really demanding too much, but to prove theorems, mathematicians, you need assumptions. Can we guarantee that if you give me a dynamical system which is chaotic, to guarantee the existence of a unique invariant measure? And the answer is no way, Jose. Not correct. It's enough to have two fixed points on the attractor, two steady states, then each delta at each one of them is an invariant measure. You have two of them, but even more than that, any convex combination of them is also a probability measure, so you have infinitely many of them. So it is not unique. What do you do then? Okay? What people have been doing, and you open the literature and flooded with these things, and people think that if you do it, then because it's more complicated, it's enough to add random noise here. Then the stochastic differential equation guarantees you an ergodic measure which is unique. That's why people put noise, not because it's more complicated, because it gives them the unique measure they want at hand. Okay? So if you want to deal with the deterministic case, you have to lose your hair, like I did. Okay? But the minute you put something random, some white noise, then usually you get unique invariant measure which is ergodic, and then all what I told you is nice. And that's why the literature is loaded nowadays with, oh, let me put white noise here just to show you it is more complicated. Well, if you don't know stochastic stuff, then the minute you see stochastic, you go the other way. Okay? The way some engineers, when you talk about function analysis, they go the other way. So we see stochastic, but stochastic is helping here. Okay? However, what happens if you don't have unique measure? Now, of course, we can end the story at here and then we retire and we'll be happy. But there is a field of mathematics which is beyond differential equations. And this is called inclusion equations, inclusion differential equations. So for every measure here you give me, I can take the average and I have dx dt belongs to a set of vector fields. And therefore, you can still continue with that. So it's not the end of the story. It's a proposal, which is going to be basically a work to be going in this direction. So maybe in reality, we have two things. Either we have to find a physical mechanism, selection mechanism, for which measure of all this zoo of measures is the most relevant to the physical process. And we know many phenomena in PDEs, they don't have uniqueness, but there are physical selection mechanisms for which one of the weak solution is the most physical or relevant. Or we have to deal with differential inclusions, and we shouldn't be shy of that. I mean, this field of mathematics is very well developed. People use it in control theory all the time, and so on and so forth, and in economics, and so on and so forth. Therefore, maybe we can roll sleeves and move into new era of numerical analysis of inclusion maps, not only, or inclusion differential equation, not only just has to be differential equation, and so on and so forth. So this is just a side comment. So now the question is, because this is basically what I advertised at the beginning, what if I don't have separation of scale variables? What if I don't know who is fast and who is slow, like as I told you in the case of Boltzmann? What can I do? Meanwhile, I gave you this beautiful background and told you about measures and so on and so forth. So in many interesting applications, we do not have separation of state variables. Therefore, one might have to identify slow functionals, observables of the state variables, and find efficient algorithms to compute them. Need not to be combination of the state variables. Maybe it is just basically you have to go outside. You have to look at it from different words, like measured on the state space, or functionals on the state space, in order to identify them. And maybe the state space has like maybe 10,000 variables, but the slow features of it, maybe 3 or 4 quantities only. And that's all what you need can compute. You can have so much variables, like basically as you told, molecular dynamics is infinitely many, 10 to the power whatever, number of particles moving like crazy, with the different velocity, different x's, but then you get at the end only 3 equations for the 3 moments. They happen to be PDEs, but that's a different story. Okay? So therefore, I mean, maybe you have to reduce, and that's the whole idea, reduction. You need to reduce the complexity of the problem to something you can compute. So I cannot solve all the problems in one day. So I'm going to focus on the next level of complexity, which is I'm going to look not into the case when I have separation of state variables, but I'm going to look into cases in which the vector field is decomposed into fast component and slow component. Notice now, it's not x slow and y fast. The vector field, all the right-hand side, has fast and slow situation. An example that, so as I told you, I advertised that I work on Navier-Stokes and fluid mechanics as a case of study would be, take the Navier-Stokes equation, which is basically an advection equation, and so on and so forth. This is the slow term, if you like, and the rotation, because the Earth is rotating relative to the shallowness of the atmosphere and of the thing. This will be like the Coriolis force. It will be the fast quantity. Therefore, I have such a situation where the right-hand side could be slow plus fast. This is just to make propaganda. There is something that we have in mind. In the case of Navier-Stokes, the rotating fast is linear, and therefore the linear case is not too complicated to deal. But I'm going to talk about general theory in which the vector field, the right-hand side, has a nonlinear, could be fast component and a slow component. What can I say? Notice that my previous case can be also decomposed into here, because the vector field for x can be x, 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 and zeros, plus 0, 0, 0, 1 over epsilon, and the y's. And therefore, it's sum of 2 components. So it is exactly within this framework. So this is a little bit more general, one notch more complicated, but I don't know which of the u's now is the fast and which of the u's is slow. So this is a theorem which is together with the Artstein, Yanis Keverkidis, and Slimrod. So assume I'm looking at this dynamical system and denote by u epsilon the solution of these equations, which are functions. Now, as I told you, I don't know, because if u has some components or features which are fast and slow, maybe in general I should not expect u epsilon to converge as epsilon goes to 0 to some function. In the previous case, as I told you, if u x plus y, the x component was converging to a function, but the y component was not converging. Therefore, I have to basically put the hat of the generalized notion and guarantee that the u epsilon converges but to a measure. So I should look at the u's, their limit, not as functions but as measures. I should look at the u's epsilon as delta measures supported on these trajectories in the phase space. And these trajectories are oscillating like crazy and all over the place. And look at these delta measures, what about their limit? So we can guarantee, under circumstances, there is a subsequence that converges to a Young measure, because we don't know that the convergence is a unique invariant measure in advance. If I put some random stuff, it's guaranteed. And that's why people put like your plus white noise, and I'm in business if I want, okay? But I'm avoiding that. I would like to show you what are the subtleties. Just enough to put a little bit random noise, and then you don't need subsequences. Everything is nice, and you converge to unique, invariant, ergodic, all the nicest stuff, all the nice features. So, because noise is stabilizing in this case. So it converges to a measure. Moreover, for every time, fixed time, this invariant measure, this limit of this, which is a measure, it happens to be invariant measure for the fast part. See, there's the fast dynamics and the slow dynamics. It is invariant measure for the fast dynamics. It's exactly the same structure that we had before. You converge. Now the question is, what can I do with this? Yes, I identified the limit, because I told you the first thing is basically I need to identify that what is the limit. So the limit is a measure. Now, how can I use it to compute with? At the end of the day, I would like to use basically, I would like to compute with this quantity. So the questions are, can one still identify some slow features of the above system? And as I said, from experience with other physical systems, the search need not to be limited to identify slow components or slow state variables, which might not even exist, these slow components. Okay? And the next question, can we develop efficient numerical algorithm to compute these slow features or these quantities that I mentioned? Okay. Now, if I go to here, to this system, and I would like to look for, identify or guess or propose some quantities which could be slow. Now notice I have U, I don't know how to compose. I have a whole U. I don't know which one of the components slow or fast, maybe they do not exist. I look for features, for functionals of the U variables. Can I identify some functionals which are basically, notice that it is basically fast component and slow dynamics. Some functionals which are really going to be moving slowly. And of course, the obvious guess or the trivial guess is, let us look into the constants of motion of the fast dynamics. What I mean constants of motions? Basically, they are integral of motions. They are not moving. Yes, you have fast dynamics. The U is going very fast. But a constant of motion is constant, not moving. Like the energy of the fast dynamics. It's constant if it's like Hamiltonian or something like that. The dynamics in the phase space spinning like crazy, but you're living on a manifold of constant energy. So the energy is not moving. So all the constants of motion of this are not really moving fast. They are standing still by the fast dynamics. However, there is a slow component because they are not necessarily constant of motion of that. They will be drifted. So imagine that you have energy surfaces of the fast dynamics, like in Hamiltonian case, and then when U is moving, U is going to be spinning like crazy on this manifold, but the G will move you from one manifold to the next one, to the next one, to the next one, to the next one, and so on and so forth. And therefore, now I see how I'm going to move between the different energy levels of the fast dynamics. And if you have more than constants of motion, then these are candidates for slow observables of the full system, which are going to be drifted slowly by the slow dynamics, even though you are spinning very fast. And the question also then, how can I compute them? First we identify them, now how we can compute them. And this is consistent with the picture I mentioned at the very beginning. I have the Boltzmann equation, or the molecular dynamics, everything is moving, but there is a measure, and the measure I cannot compute, but certain moments of the measure are moving slowly. And I have equations of motion for them which happen to be closed. And that's basically, as I told you from the very beginning, this is the metaphor I have at hand, or at head in some sense, that I'd like to keep in mind, that maybe the system is too complicated, the U is too complicated, but some features of it, I can really do something with it. So the slow observables is the constant of motion. Too fast. So the constants of motion of the fast dynamics of the above system are candidate for the slow observable, and the idea is to find equation of motion and how they are drifted by the slow dynamics. So suppose in U, or V of U, is a constant or functional of U, which is like constant of motion for the fast dynamics. So which is for every solution US, the UDS, this is no, actually it should be F here, there is a mistake. They satisfy this relationship. This is not F. This is F supposed to be. The fast dynamic is F. This is not G. So therefore they are constant of motion. Therefore they are equal to 0 whenever G here is F. Observe that whenever mu is an invariant measure for this quantity, then U in U is a constant of motion for it there. Therefore, it's constant supported on mu. So mu is supported on this in this particular thing. If we denote by this value, which is with respect to this support, this quantity, then one can show the following theorem. As I told you, the U epsilon is converging to a measure, mu 0, and therefore the constants of motion on the support of the level of this measure, satisfying exactly this differential equation. This is the way they are drifted, because they are constant of motion. You look for the gradient. And we look for the gradient, that's basically when they are changing. And you look how they are drifted by the slow dynamics. And you average them with respect to the invariant measure. So this is the equation of motion. This is the equivalent of dx dt is the integral of f of x y d mu dy. But I don't have now x, I have a constant of motion. And therefore, they are basically moving according to this particular equation. That's why I gave you this background, so you can see the analogy, but this is the upgrading version of that particular analogy, and this is the equation of motion for this particular thing. Now, the question is, how do I compute with this particular thing? So I'm going to give you hand-waving the algorithm, and I'm going to show you some computational results in the next few minutes that remain for my time. The idea is the following. You give me, I know these functions v's, you have to give it to me explicitly, okay? These are the constants of motion, like energy, the momentum, something for the system which you have at hand. And I'm going to give you an example which is loaded with such constants of motion. Not only one, not only two, a lot of them, okay? So I'm going to take one of those, and I need to, I compute the gradient of this quantity. I have explicit formula for it. I have a g, I have explicit formula for it. All what I need is the invariant measure here of the fast dynamics, and assume it is like unique. Therefore, I can represent it, because it's unique, I can represent it by time averaging. So I'm going to take this quantity and go simulation with the fast dynamics and average it. And therefore, this will give me the right-hand side of the time derivative. If I know the right-hand side, I can use some numerical differentiation, advancing, and then advance this slow quantity, but I can take the time step large. And now I repeat the same procedure, average, and then jump fast, and then average, and then jump fast. And that's basically the gain in the efficiency is by this large jump, because I know that this quantity is moving slowly. The work will be in representing the measure, in sampling the measure. And this is by computing only the fast dynamics, but the time is rescaled because I'm looking for an invariant measure, so I don't need to put the epsilon, therefore I can use. But I need to do lots of steps to sample it correctly, and that's basically the upshot of the whole thing. So let us now move into an example. This is the example I have at hand. It looks complicated example, but it should not be. So let me tell you where is this example coming from. This example is coming from very simple PDE, and this PDE is very famous. It's UT plus UUX equals epsilon UXX. This is the Burger's equation with viscosity, okay? So this is the Burger's equation with viscosity, and now you need to discretize it. So I need to discretize it. I do second order scheme for discretizing the UXX. And now the question, how do you discretize UUX? And this is a whole game. UUX, you can discretize it many ways. You can put UI as second difference is the second order scheme here, or you can think about it as U square over 2x, and you can basically do differencing here, or you can take combination of the two, and so on and so forth. This specific discretization, UK plus 1 minus UK minus 1, any of you, because there's this loaded this room with numerical analysts, they know very well that we don't use this discretization for Burger's equation. Except if you are Peter Lax, you are allowed to do anything you want, okay? So Lax and Goodman investigated this specific scheme, because in particular this discretization nonlinearity, if you do the Taylor expansion, it will be not only approximation of U, it will be approximation of U, UX plus H square UXXX, maybe divided by some constant here. This is basically approximating more, not only of the advection, but something with 3 derivatives times U. It is more dispersive scheme, like closer to KdV, and that's why this scheme is really having lots of oscillations, and the goal was to understand what's the reason for this oscillation, what triggers them. And what triggers them is the dispersion, these 3 derivatives, because this is better approximation for this nonlinearity rather than this nonlinearity. However, still, why we basically chose this specific discretization? We chose this specific discretization because, as you can see, the fast dynamics, this is the fast dynamics, the 1 over epsilon. And this is the slow dynamics from the diffusion. I would like to see how does the slow diffusion affecting the advection of the quantity. Now, if you look to the fast dynamics, namely, forget about this particular case. You look at this equation, it happens to be equivalent to the Toda lattice. And if it's equivalent to dot lattice, the lattice is an integrable system. And if it's an integrable system, has gazillions of constants of motions. So not only one, not only two, not only three. So we chose this discretization to demonstrate the power of the machinery. I didn't want basically to give you an example to compute only the energy and the first momentum, and then it says, oh, that's all what you have been doing, all this work, so you can show me two quantities. Now I have an equation which has lots of conserved quantities. In fact, if you have n dimensional, you have n over 2 constants of motion. I can compute them all. And all of them are constant of motion, all of them are slow observables. Okay? So it's a rich example in that sense. That's why we have difficulties publishing this paper. Because people say, oh, you're discretizing burgers at the end. But people miss the point. The idea is we want to give an example to show that the theory is rich. In any case, so this, as I said, has been investigated by Goodman and Lax. And it's an integrable system. And therefore, if you have the integrable system, you have the Lax pair, you can generate, even using like algebraic computations, you know, in the computer to generate these constants of motion by the Lax pairs. You don't need even to find them by hand. Now you can put it in the computer and you can find them by symbolic manipulations. You can find them all. Okay, so it is honest to goodness, fully computational, and then you can find them. So it's together with Belgier and Arstein and Kivrakidis and Slimrod. We use this Young measure approach in order to compute these constants of motion. So this is a torus, just to show you. We took n equals to 6. So this is for the fast dynamic. You can see you have an invariant torus. This is for the fast dynamics, and that you know that the dynamics they use are going around, so they are chaotic. Now this is the first component of the solution. You can see it's oscillating, so it has some fast features. Now, if you look for the gradient of the third component or the third invariant times the g, you can see that it's very oscillating in time. That's why you need to do averaging. Remember, it's supposed to be the averaging which is advecting this low quantity. But if you take it point by point in time, you can see it's oscillating like crazy. But you have to average it, because you have to average with respect to the invariant measure. So we average it in time in this particular case. And you can see that when you average it in time, it's not as oscillatory. It's like basically behaving nicer. And now, the constants of motion, their evolution, you can see that it's very smooth. 3 constants of motion, we can see that basically different constants of motion, they are moving very slowly. And now, if you look for the invariant tori that I told you and see how they are drifted by the viscosity, you can see with time that they are shrinking and shrinking and shrinking, because viscosity makes everything shrink. And I think I'll stop here and take questions. Thank you very much.
So now we have heard the proof of the TT know-how theorem, and we have time for questions. Thanasis.
In the transparency before the last, when you saw the averaging of this quantity, which was really very nice, is this before that? There, is this generic or is it because the system is integrable?
No. The whole idea that this is
Generic.
This is generic because this is an average quantity. This is a slow. Here's the point. This is a slow-moving quantity by the theorem, because it's a constant of motion. So therefore, the average with respect to the measure supposed to be not large, supposed to be order 1 quantity and drifting slowly this quantity. Yes.
What are your assumptions on the theorem for the ODE 1 over epsilon f plus g?
What the assumption?
Yes.
The assumption is basically that you have a compact attractor in U epsilon, and therefore the U epsilons are bounded, and therefore they converge. Now, that's why you have subsequence converging to a measure. Different subsequences might converge to different measures. And this is, we don't have the uniqueness of the measure. That's basically the whole thing. But otherwise, we don't have any problem.
If you're in that framework, then you don't need actually to use these effective equations.
Which effective?
The one related to the conserved quantities. If you just switch on and off the stiff term 1 over epsilon, this allows you to take mesosteps or core steps. And you can actually...
Yeah, I know. There is some papers about that. There's something which is Martin and company have flavor. I can have another lecture show it doesn't work. Because even direct numerical simulation does much better. You have to tune it so nicely to work. I give you examples I have, but I didn't want basically to show things which are not working. I want to show something which works. So if you take this one goes like slow, large, slow, large, slow, large. I have an example. All these limit cycles ones, even direct numerical simulation does better than those ones. I mean, this is numerical experiments. And I have a whole lecture about that, but we can talk. I'm here for a whole week, so I can show you this. I heard about these things that you can do small step, larger step, small step, larger step. If you don't sample the measure correctly, you are drifted. When you are drifted, you are really going to the wrong place. You have to sample the measure correctly, and that's if you don't sample it enough. So if you do like fast one and then go like big step fast, you can jump on different leaves of things, and God knows what happens. And that's basically where we show. If you don't tune it carefully and carefully enough, you get completely the wrong answer. And by that time, direct numerical simulation does the same amount of work more accurately and for the same cost.
Yeah, well, first of all, thank you for this wonderful lecture. Now I have two points. One of them is when you want to advance this V quantity, you have to average,
Yes.
and this you do by sampling the fast dynamics.
Yes.
If the fast dynamics lives on a high dimensional torus, do you have some clever trick to explore these torus in an efficient way, or you just
So far, we were just pedestrians. We didn't do it. You know, we were doing it like the peasant way, just straightforward. We didn't use any extra further reduction.
Okay, and then another point is, you said that your candidates for these V observables or functionals or quantities are constant of motions of the fast dynamics. Isn't it true that only constants of motions of the fast dynamics can be reasonable candidates to slow observables?
I don't believe that, because it could be just by miracle that some quantity which is slow for the fast dynamics, which happen to be not constant. How? I don't know. There are some, not everything which is like moving slowly by the fast dynamics must be constant. It could be just miracle that there's some quantity which is moving slowly, but not necessarily constant.
Okay.
But that's what I say, these are candidates, but might not be the only quantities. But for sure here I know that they are working.
But do you have an example, or is it just?
No, I don't have a specific example, but if you are interested and you're willing to publish it, I'll cook it for you.
Where you want me to publish
No,
it?
I'm
I
just
don't publish it.
I'm just kidding. I'm just kidding with you. No, but we can cook such examples. I think we can cook such examples.
Okay, last question.
Have you tried this on the Fermi pasta ulam problem?
Well, we didn't, because everybody doing Fermi pasta ulam, and we wanted to be a little bit original. Otherwise, somebody tells us, well, I mean, you're doing the same thing. So, but we, pardon? Okay, so we'll do it, and I will send it to you. He doesn't want to publish. Maybe you'll publish it. Well, thank you very much. I appreciate it. Thank you.
Thank you.